Hey class, you remember a long time ago when we talked about the trig derivatives? How to get those? So there's this unique little equation formula I kind of put in there for you guys because it helps. It's called the Pythagorean identity. Probably heard of it before. Most basic form is going to be sine squared of x plus cosine squared of x is equal to 1. Where generally, or always, x is equal to an angle measurement, whether that be in degrees and radians. Usually in calculus we're working with radians. Radians are kind of the universal unit for angles. Degrees used a lot in physics, I know, but in calculus here we're going to learn everything in radians. There might be a few exceptions I talk about in the future that involve degrees, but not really. But I think it's important to understand where this equation comes from, and all in general kind of equations I give you, I don't want to just throw them at you and expect you to just say, hey, this exists, I'm going to accept it as fact, memorize it, and move on. I thought I'd like to say just, hey, where does this equation come from? Because it's not terribly difficult, right? It's a right triangle equation. So I'll draw out a quick right triangle. Sides A, B, C. C is your hypotenuse. I'm going to draw angle X here, and just indicating that's a right triangle, right? So sine squared plus cosine squared of x equals 1. Now, the most basic way to kind of prove this is to first ask, okay, well, what is sine squared plus cosine squared actually equal to? What does this mean? We know it's equal to 1, but this is where we're going to start out, because originally when, doing a proof, you don't always know what your end goal is. You don't always know what some expression here equals in equation form. But we do. Well, let's get there. So, expanding sine squared and cosine squared, we can say this is equal to, oh, and I forgot to write my x's. Sine squared of x, angle x, plus cosine squared of x. All right, because it is important that we are talking about x here, and it'll make sense. Sine is going to be your opposite over hypotenuse ratio. Ratio of this angle is going to be, ratio of your sides. So sine squared of x is actually going to be b over c squared. Right, I just kind of evaluated, given this is x, angle x, opposite over hypotenuse. Okay, squared that. Plus, and we're going to do the same thing for cosine. It's going to end up being a, our adjacent angle, over hypotenuse, and all that squared, right? Okay, now from here it's pretty simple. I'm going to distribute this exponential inside of each fraction to the top and bottom variables, I guess you could call them. It's going to equal b squared over c squared plus a squared over c squared. Okay, because we can do that. There's no addition or subtraction inside of our parentheses. We can distribute in those exponents, right? From here we have a common denominator. So we can combine these and get a squared plus b squared, and I reverse the order there, because if you see it, you'll know now why it's called the Pythagorean identity. We have right here a squared plus b squared. And what does a squared plus b squared equal? If a and b are our non-hypotenuse sides of a right triangle, well, a squared plus b squared equals c squared, right? That's Pythagorean theorem. So this whole fraction here is equal to just c squared over c squared, which is just equal to 1, right? And so that's where that comes from. In case you were ever curious, of what this equation means. If you already knew it and I sound silly, okay, skip this video. Sorry for impeding on your time, but I think it is important to understand where our equations come from. And and this one comes from the Pythagorean theorem too, right? Which Pythagorean theorem is not super hard to visually show you why that works, right? We start off there with a squared plus b squared equals c squared. I think the easiest proof for that I can think of is, and I'll kind of draw this pretty roughly. Start off with a square, right? We're going to draw two identical triangles. I'll draw them in red here. Here-ish, kind of like this. We're going to have a hypotenuse C. This is going to be like a little side length B here. It's going to be A. Okay, now we do the same thing here. We make like little squares. We make two triangles. These are completely identical triangles, slapped right next to each other, squished together. Okay, so we have side length A, side length B, and we're going to do the same thing over here. And clearly this isn't drawn to scale. How does this go? Yeah, it goes this way. My apologies. That's C, even though those clearly do not look equal. And then I'm going to draw another side, B. This is also B, and this is also A. And so what we see here with these two squares that I just drew is that this little area here is equal to A squared. This little area here is equal to B squared, right? And now, fun thing, if we were to take these triangles, let's say I use like, like a compass, a straight edge and all that, to draw these perfectly, accurately, precisely, what would end up happening is if we rearranged our triangles so that our AB right angles were one of the corners of this square, and I'll kind of try to draw that out here, and just over this with black. Have like A kind of like this, and then like B here, then you'd have C here. C is this, oh, I drew that really bad. Oh boy. You'll see in a second. Okay, this is side length C, this is hypotenuse. You do the same thing here, and this is where I realize that I'm like not correct about this. Okay, that's C. Let's kind of ignore that. You do the same thing up here. You have side length A, and then you B, okay, and then C, and these connect, right? You have side length C again. And you do that with all four of the triangles you've created. This is not a square, this is a rectangle. You get something that looks like this, right? And this proof is probably all over the internet. You can see somebody that's better than me at drawing this out. But you'll see what happens here. These are still the exact same triangles, rather. Move it, yeah. This last one's the weird one, because I drew this first triangle so poorly. It'd more so be like that, right? And then we could have our last C side here. And I believe this is A and this is B. Sorry, I'm drawing this square super wrong. But then what you see here is that we have now this square. We use the exact same triangles, and that ends up being the area of C squared, right? Since we changed nothing about the interior of our square or the area of our actual triangles, nothing about the side lengths of A, B, or C, we've visually proved that A squared plus B squared does equal C squared. Yeah, sorry for my poor visual proof there, but I hope that makes sense. If you're interested, go look up this, it's like the square rectangle proof on the Pythagorean theorem. It's not super difficult, but it's cool. With some geometric shapes proves the Pythagorean theorem, which is so fundamental. And here, Pythagorean theorem, we use that to prove our Pythagorean identity for our right triangles. Sine squared plus cosine squared equals 1. Last thing, quick reminder as I erase all this, our original equation up here, you can divide both sides by sine squared and cosine squared to get new forms of the equation. And I talked about that in the trig derivatives video. I'll go over it again real quick. So if you divide the whole thing by sine squared of x, right? Yes, if you divide the whole thing by sine squared of x, or I guess multiply by 1 over, because that's how I like to think about it here. And then we'll multiply this by 1 over sine squared of x. Right, because now I like to think about how I can just distribute this in, right? It's going to be 1 plus, okay, and then cosine squared of x over sine squared of x, that's cotangent squared of x equals, okay, now 1 over sine squared of x, that's cosecant squared of x, right? And then same thing, if you multiply this whole thing by 1 over cosine squared of x instead, or just divide both sides by 1 over cosine squared of x, you end up getting tangent squared x plus 1 equals secant squared of x. So, all right.